We now move on to the final section, which is, I think, actually the most interesting, which brings up the question of how can we improve the available tools in the Python ecosystem. What can we do to make them better, and also to incorporate new ones that would be really useful. And I'll start off with some of my efforts, and in particular I want to focus on the spherical Voronoi diagram, which is something I've been working on for several years, largely because I work on spherical viruses, and we want to be able to parse out the properties of these viruses in terms of, for example, the amount of surface area that each of the protective molecules on the surface of the virus occupies. But it turns out that actually the primary application for this particular algorithm, at least at the moment, is probably more heavily geared towards geographic information systems. So, for example, calculating the appropriate search and rescue region, which airports are closest to a particular search grid. Looking at, for example, the surface areas of different territories, so different states, different provinces, different basically country-based divisions within a given country. This can be used for in a much more accurate fashion than, say, a planar estimate of the surface area of that region. So this is actually a sort of fairly long-term collaboration between the mathematician Nikolai Nowotchik and I. So he was working at Imperial for a while when we were collaborating on this, and it took quite some time. I mean, the initial project was a sort of a few years of giving seminars and getting advice from mathematicians, and then eventually I met Nikolai and we decided to actually make it happen. Thanks also in part to some input from the developers of Seagull. So they had considered the possibility of implementing this algorithm, and they did actually know at least how to implement the quadratic time complexity version, which is the one that I've incorporated into SciPy.spatial. Note that this won't be available until SciPy 0.18, which is likely won't be out for quite a while. I think we're just about to release SciPy 0.17.1, so it's still quite a ways away from 0.18. But I've built the master branch for the purposes of this tutorial, and you're always welcome to build the master branch if it's not too much of a pain for you, so that you can use this code. So yeah, there's many other applications. I mean, there's geographic information systems. There's also astrophysics. So if you wanted to know, for example, the surface area of the methane lakes on Titan, the moon Titan, I get emails occasionally from MRI scientists. They look at roughly spherical objects that are often decomposed into constituent polygons. So they have a need to tessellate the surface, and they're also interested in calculating the surface area of those polygons, which I'll discuss in a little bit. But certainly the fact that this is only quadratic time complexity, and there are several known algorithms that do a log linear spherical Voronoi diagram. This means that there's actually considerable room for improvement for SciPy.spatial within the Python community for spherical Voronoi diagrams. Now that said, I did actually try initially. I went, of course, for one of the optimal algorithms, so the log linear time complexity algorithms. But after several months, I just had to sort of make the decision that enough is enough, and I'll try to implement the quadratic time complexity so that we at least have something that works as a starting point, because it was proving actually quite difficult. And my particular approach was actually one of the algorithms presented that was based on the idea that you do stereographic projection. So you start off with your data on a sphere, you project it down to a plane, then you basically do a Voronoi tessellation in the plane, and then project the data back up to the sphere and perform a set of geometric operations, and then project the data back onto the plane again, calculate another Voronoi diagram, and project it back up to the sphere a second time. So as you might imagine, the steps in that algorithm are highly non-trivial, and we just couldn't get it to work. So for now, this is the best we have, but I think you'll find that it still seems to work pretty well for a reasonable number of input generators. The other thing worth mentioning now that we're working with spherical data sets is that the generation of a random set of input points is actually non-trivial. So there's a few different algorithms that allow you to sort of effectively produce a pseudo-random set of points on the surface of a sphere, but a sort of naive point picking approach would actually tend to bias your picking towards the poles. This is basically based on the trigonometric distribution of points on the surface of the sphere. So you just have to be careful to use one of the well-known algorithms. So there's a few different sphere point picking algorithms described on Wolfram's site, and the Mersegli approach was particularly appealing because I can implement it in a fairly straightforward fashion using numpy.random from a uniform distribution. And here we're dealing with a unit sphere, so from a low of -1 to a high of +1 for the radius values. And we effectively just return an array of x, y, and z coordinates. So we're just stacking them here because we've produced each of those three columns separately. And here we're going to work with 600 generators, so 600 random generators on the surface of a sphere. And you can see that we've used, right here, we've used this brand new scipy.spatial.spherical Voronoi on the input data points, specifying the radius. And also important to note that we use this sort vertices of regions method. You don't have to sort the vertices if you don't want to. So if all you want to know is the coordinates of the Voronoi regions, so you have your input points here shown in blue. If you just wanted to know which Voronoi regions or which Voronoi vertices were where, you wouldn't have to do any sorting because you could just plot them. But most of the time, and certainly most of the time that people email me with questions, you'll want to actually have the Voronoi regions properly ordered, so you'll have the polygons available to draw around, as you see on the right over here. So typically you'll want to sort the vertices of regions because of the need for plotting and also for surface area calculation of those spherical polygons. So we basically iterate through the regions, and so the regions are, I think these are indices, yes, because I've indexed the vertices, which you can easily plot without sorting, and then taken these regions as a basically sorted version of the indices that will give us our polygons with ordered vertices. And so we effectively just do this one region at a time, generate the polygon, and then progressively add polygons to the 3D collection of spherical polygons, and plot that data. So here it actually looks like we're doing a pretty good job of the plotting. So these actually look like they're proper spherical polygons that are curving on the surface of the sphere. That's only partially correct. So if we were to have, say, 5 input data points, the output would actually look much worse. And this has to do with the way that Matplotlib is dealing with the surface curvature for these polygons. And that's actually another area that can be improved, and I'll discuss that in a few minutes. But certainly this looks like a sensible tessellation. And you can again imagine that each of these different colored Voronoi regions or different colored tiles is, for example, the airspace for around a particular country, or network coverage, or some kind of marketing or shipping coverage. And so all kinds of, even epidemiology, if there's a global virus outbreak and we want to know which regions are closest to a particular outbreak epicenter, again, the Voronoi diagram can be very useful for that purpose. And I think I'm a bit biased, but I think it's actually quite useful that we now have a way to do this in an open source fashion using Python. So now moving forward with the idea of calculating the surface areas of these polygons, this is also sort of a way to assess the output of the spherical Voronoi code. So for example, if you have your data is effectively covering a perfect sphere, and you add together the surface areas of all the constituent Voronoi regions that come out of that analysis, you would expect, if everything works perfectly, that you would completely reconstitute the surface area of the sphere as the sum of the surface areas of the constituent polygons. So the code I've used for this is not available in any mainstream library yet. I've opened an issue to integrate it into scipy.spatial eventually, but I think this is sort of a more long-term concept because there are still some issues to iron out. And Ed Edmondson, a scientist at the University of Portsmouth, kindly reviewed my code after I gave a talk in London last year. So he's certainly improved the performance and the correctness of this spherical polygon surface area calculation code. And you can see I've actually just pasted the code in that we've been using. So there's some utility functions to convert between Cartesian and spherical coordinates, which is quite useful in certain aspects of the calculation. There's also the special Haver sign distance, which is calculated between the points. Basically, it's the distance over the great arc of the circle between given points. And then we also have this function which does actually calculate the surface area using what's called Lulli's theorem. So you basically decompose into triangles. So again, the concept of triangulation, even on the surface of a sphere, even in 3 dimensions, this concept of decomposing into triangles and calculating properties of those triangles is quite useful. So again, leveraging the power of triangulation for more advanced calculations in 3 dimensions. So the algorithm probably could be written more nicely and vectorized and all these sorts of things. But for the moment, this is the best that we have, and it seems to pass a number of unit tests. We'll just execute this cell. And now we're going to go down here, and we're going to work with the regions that we had before. So for the initial 600 input data points on a unit sphere, and we're going to compare that with the surface area of a theoretical surface area of a unit sphere, which is 4 times pi times the radius squared. So in this case, 4 times pi. We'll just recalculate that to make sure it's working properly. And in fact it is. So we have a calculated surface area of about 12.56 and a theoretical surface area of 12.56 as well. So it looks like both the spherical Voronoi diagram calculation and the assignment of regions has worked properly, and so has the reconstitution of surface areas. So that's certainly a sensible result. And that said, there's still a few sort of issues to be resolved. So if you think of the cases that might be a bit pathological, for example, you might have all of your data points in a single hemisphere, or just one point at the antipodes, at the poles, at the North Pole and the South Pole. Those cases are often pathological. So understanding exactly which cases are pathological is still a bit mysterious to us. And in terms of the surface area calculation, if you have a polygon, a spherical polygon, which effectively covers an entire hemisphere, that does appear to be a problem. So I think we need to be able to basically say, what are the limits of this polygon surface area calculation algorithm? What's an acceptable input and what isn't? And decide on how to handle those situations and make sure that those limitations are match with the theoretical limitations of Liouville's theorem. But at least we're in a position where we now have something that seems to work most of the time for most sort of normal/random input data sets. But I'm sure you could cook up quite a few sort of artificial cases that are quite pathological, and we don't have a full handle on exactly what the precise limits are. The other thing I've been thinking about, and this is sort of described in the issue for this particular code, is the problem of vectorization. So because the idea with with NumPy, if you have something, for example, you have a random set of data points, so say 3D points equals numpy.random sample, let's say 25 points in 3 dimensions. Oh yes, I should not be using a number to start off my variable name. So we'll call it points 3D. And we'll check the shape of points 3D. So points 3D dot shape. So that looks sensible, right? We basically have 25 three-dimensional coordinates. And if we want to take the square root of basically every value in that system, we could easily use so square roots, a numpy func, so universal function, so numpy.square root, and then put in points 3D. I think that should work, if I'm not mistaken. And if we take a look at square roots.shape, for example, so it has the same shape, right? Because the idea with these numpy universal functions is that they operate on basically each element in the array very quickly. But the problem with polygons, if we wanted to, if we presumably wanted to leverage the fundamental vectorization scheme in a similar fashion, is that polygons can have heterogeneous shapes, right? So our input data might look like 0, 1, 2 for one polygon, and then 0, 1, 2, 3, 4, 7 for another polygon. And then we have our, so we have our input array is equal to numpy.array of that. If we take a look at this input array, the data type is object, and I mean generally there's no simple, as far as I know, it's not, at least not as easy to vectorize this particular data structure where you don't have these sort of rectangular, the guarantee of rectangular structure. So if we try to do a numpy.square root on that, yeah, you can see that actually, the way that this is being broken down is not amenable to vectorization, at least not in this particular structure. So I think effectively we have just these two lists instead of having these actual NumPy arrays that can actually be used with broadcasting and universal function vectorization. So I'm interested to know, especially for people who are much better at vectorization than I, and dealing with the C code or the Fortran code or whatever is decided, whatever gets decided to be used in this particular case, if there is in fact a strategy that would allow for very rapid execution and vectorization despite the heterogeneous data structure of polygons with sort of arbitrary numbers of vertices. So that's one potential area. If you have skills, certainly many of you may have skills in that particular domain that I do not, where you could actually make a really valuable contribution. Because people certainly email me and they ask me about how do I calculate the surface areas of these polygons, and if we have a faster way to do it, I think a lot of people would appreciate that. So I'm just going to mention, I think, one or two more ways that I'm aware of that the sort of ecosystem could be improved. These are not things that I'm directly working on. I know my colleague Nikolai is working a fair bit on something that we identified fairly early on, which I've just briefly alluded to, which is that the way that Matplotlib handles the plotting of spherical polygons is actually quite crude, so it won't actually properly triangulate them and produce a nice curved surface. And so this is described in this Matplotlib issue, and Nikolai has opened a pull request, and I've put in a few comments there just in terms of my own testing. And so here we're going to work with 25 random points on the surface of the sphere. So the previous example worked with 600, and now we're reducing that substantially so that we can actually clearly visualize the weaknesses of the algorithm. So here you can see, we can execute it a few different times and get different results, but in all cases, we're basically going to get something that barely looks like a sphere. It's more like a blob, and clearly the triangulation and the sort of extrapolation of the curves has not been done in a manner that clearly convinces the reader or the observer that we actually have true spherical polygons here. So we do, it's just that they're not being properly plotted. The coordinates are correct, and the surface areas are generally calculated correctly as well, but the plotting needs some additional work. I have noticed some, so I think I linked to this issue in the discussion of some of these problems, and also there are questions like can Matplotlib ever reasonably handle the case of, for example, an entire hemisphere? So again, even in the plotting scenario, we need to know what the limitations are going to be, if there are any specific limitations in terms of what can be reasonably extrapolated and triangulated into a reasonable looking spherical polygon. But I think that's also quite important, because if people are working with with large areas, for example, on the surface of the Earth, and you want it to look at least reasonably reasonable, then there's certainly a motivation for having these plots produced in a very clear fashion. And the other thing, of course, worth mentioning is that, of course, our planet is not a perfect sphere. Most of the viruses that I work on are not perfect spheres, and many other planets and suns and so on are not perfect spheres. So there's probably a substantial motivation for also developing tools for tessellating three-dimensional ellipses and other kinds of sort of oblate deviations from sphericity. A lot of the algorithms, the underlying algorithms, may be out there, but some of them may not. So it may be a sort of waiting for advancements in the pure mathematics, and then progressively incorporating those into the Python community. Certainly for things like cylinders and a few other shapes, I think there are actually some nice algorithms out there, and certainly I think there are also cases where people will want to calculate that And of course, you probably have ideas that I haven't thought of, and I think given the fact that my formal training isn't in computational geometry, and I've still with the help of a number of sort of advising and collaborating mathematicians, I've managed to make what I think is at least a moderate contribution to SciPy at Spatial. And I think that if you're an expert or you like way more than I do about computational geometry, the possibility for making a really substantial impact and saving a lot of people a lot of time so they can focus on science instead of the pure mathematics is actually potentially a really useful contribution that you could make. So I'd be interested to hear what some of your suggestions might be and what you guys might be looking for.